Okay. It's a great pleasure to be here. I'm going to tell you a story that began in about 1986, probably when most of you were not even born then. It's a story which involves quantum field theory and relativity, and I know that quite a lot of you who are in the statistical mechanics school here probably don't know a great deal about quantum field theory or relativity. So I hope you'll bear with me that occasionally the equations are going to start getting a lot of indices at certain points. I will just try to make the arguments as simple as I can without going into the and just try to give you an overview of the basic ideas. So it all starts with the renormalization group, which we'll get back to in a moment. Okay, so the renormalization group, which sort of dates back to ideas of Han Wilson and others, is really one of the most amazing organizing principles of the way that we look at the natural world now. In its basic form, it just basically says that if we understand the physics on a particular length scale, which I'll call L0, and the physics at that particular length scale is governed by a number of parameters, G1, G2, which may be the masses or the coupling constants of a quantum field theory, or maybe the couplings in a statistical mechanics model, then we can if we want to understand the physics of the same system on another length scale L, we can show that by remaining at the original length scale L0, but allowing the parameters to flow according to these nonlinear renormalization group equations, where, of course, everything is buried in these renormalization group beta functions, which, of course, we would then have to calculate. But in particular, if we're interested in the infrared limit, that is what happens at very large distances, or the ultraviolet limit, what happens at very short distances, what we expect is that the physics is going to be governed by what goes on at a renormalization group fixed point, where these beta functions vanish. So renormalization group fixed points generically correspond to points at which the system is scale invariant. For example, we could think about a quantum field theory without a mass, or a gapless quantum system, or the scaling limit of a classical lattice model at a critical point. Now, that's too generic for what I want to actually talk about here. I want to talk about systems which, in addition, in this scaling limit, are rotationally invariant, or if we think of them as theories in Minkowski space, are Lorentz invariant, and in that case, this idea of scale invariance is usually enlarged to a larger symmetry called conformal symmetry, and then we have a conformal field theory or a CFT. So I won't explain this now, but if you come to my lecture on Monday, that will be explained in slightly more detail. So if we want to look at a particular system, they are going to be characterized by their possible renormalization group fixed points, which are going to correspond to conformal field theories, and the possible renormalization group flows in between them, in particular the ultraviolet behavior is going to be, or the short distance behavior is going to be described by a particular CFT called CFT sub UV, and then the renormalization group flows are going to flow us towards large distances into a generically different CFT called the infrared one. So in general, a given system may have many renormalization group fixed points and flows between them. This is an example actually taken from that green book, which are the renormalization group flows in a diluted Ising model. I'm not going to go through this in detail, but in a three-dimensional space labeled by temperature, dilution, and magnetic field, this is supposed to show that there are various renormalization groups X points. Here, we have an unstable one corresponding to the tricritical Ising model. Here we have an Ising model. Here we have another Ising model. We have very complicated renormalization group flows, even in a relatively straightforward model like the diluted Ising model. And we would like to know, in general, is there a general principle constraining such flows? For example, would it be possible for us to flow in the ultraviolet from a conformal field theory 1 to a conformal field theory 2, and then switch on some relevant operator here and flow to a conformal field theory 2, and then maybe back to the original conformal field theory. There is nothing in principle in those renormalization group equations preventing these kind of circular flows actually happening. And one thing that we will see is that the kind of theorems that I'm talking about actually say that this kind of thing cannot actually happen. So in general, what happened in 1986 or 1987 is that Zamolodchikov proved a c-theorem, it was called, which basically said that in 2 dimensions, renormalization group flows always go downhill. And by that, what he meant was that there exists a function C of G on the space of all 2-dimensional quantum field theories, so it's restricted to looking at relativistic quantum field theories. But that doesn't mean that we have to be doing high energy. For example, a relativistic quantum field theory describes the scaling limit of the 2-dimensional Ising model. Anyway, he showed that there exists this function which is decreasing along renormalization group flows, and it's stationary at each renormalization group point corresponding to a conformal field theory, where its value is the appropriate value of what's called the conformal anomaly number, which basically, although it doesn't have to be an integer, it actually roughly counts the number of gapless degrees of freedom in the CFT. So what he showed was that these flows always go downhill if you think that the height is the value of C. In particular, that implies when we have a flow from an ultraviolet CFT to an infrared CFT, that the value of the conformal anomaly number at short distances is always going to be greater than the value of the conformal anomaly number at large distances. So renormalization group flows always go downhill. So there we go. So we have basically a landscape of conformal field theories where you can think of the altitude or the height as being the value of C. So this is a photograph taken a couple of thousand kilometers north of here, and you see the conformal field theory with the largest value of C here can flow down here and then flow down here, or it could flow down here and down here, or it could start up here and flow down here. So you should imagine that the space of all possible quantum field theories is a mountainous landscape, rather like this. Okay. So, having proved that in 2 dimensions, it was obvious to try to see whether there were generalizations in higher dimensions, which and a couple of years later, in fact, I proposed a generalization which would apply to all even number of space or space-time dimensions. And in time, this became known actually as the A-theorem, even though at that point it wasn't a theorem because it hadn't been proved. And the idea was that, once again, there exists a pure number A, which is going to be the analog of Zamolodchikov's C, which is going to characterize d-dimensional conformal field theories such that along renormalization group flows, the ultraviolet value of A is always going to be larger than the infrared value And this was shown to be true for what are called weakly relevant flows, basically when the ultraviolet theory is perturbatively close to the infrared one, and seemed to be satisfied in all known examples of when we actually understood what the renormalization group flows are. So A is like C. It basically measures the number of massless degrees of freedom. And if you calculate it for a free theory in 4 dimensions, it's actually given by this strange formula. It's the number of scalar particles plus 11 times the number of fermions plus 62 times the number of gauge fields, etc. Yeah. That will may become clear or may not become clear. I can basically say the words, but the words may not mean anything. A and C are related to what are called quantum anomalies in quantum field theory, and they only occur in even numbers of dimensions. Yeah. No, that's the result of a calculation. Oh, well, yeah, there might be. Who knows? Anyway. Okay, so an example which was a test of this a-theorem at the time that it was proposed was just to consider quantum chromodynamics, or a generalization of the standard model of the strong interactions, where instead of taking 3 colors, we take n A colors, and instead of taking the usual number of massless fermions, like the up and down quarks, we take NF massless fermions. And in that case, if you use that formula, if we know that QCD is asymptotically free, so that at short distances, the ultraviolet theory is just a free theory of gluons and massless fermions. So according to that formula, A in the infrared is given by 11 times the number of fermions, which is NCNF, times 62 times the number of gluons, which is NC squared minus 1. On the other hand, if we look at large distances in QCD, we expect chiral symmetry breaking, which is responsible for giving us the pion, which is massless in this limit. So we expect NF squared minus 1 Goldstone bosons, which are the generalizations of the pion. And in that case, we just have NF squared minus 1 scalar bosons. So this conjectured A-theorem might appear to be highlighted if we make NF too large, because this goes like NF squared and this goes like NF. So already there seemed to be a counter example, but what actually happens is that when you study the beta function of QCD, then if you put too many fermions in the theory, in fact, if NF is bigger than 11 over 2 NC, which is well below this limit here, then asymptotic freedom is lost, so there is in fact no contradiction. So this was one example where there was no contradiction to the A-theorem at the time it was proposed. Now, just to go into a little history of the A-theorem, after then, Osborne showed that it could be proves sort of to all orders in perturbation theory, but because this is supposed to be essentially a non-perturbative result, that's not really enough. Then people thought about all kinds of other examples of gauge theories in 4 dimensions and supersymmetric theories and all kinds of fancy theories which were reductions of string theory, etc., etc. And it passed all these tests. And it was actually shown relative to Sid's comment that if you change the numbers 11, 62, etc., you can always find a counterexample. So it really had to be those numbers. Then there was a holographic version. It was related to entanglement entropy in 2011, and I'll talk about that hopefully towards the end of my talk. And then, remarkably, in 2011, a proof was posted of the A-theorem by Komargodski-Schwimmer, and I'll spend a little time trying to describe to you what the elements of the proof are. One, I've always put the word proof in inverted commas because this, I want to stress, this is a theoretical physics proof. It's not a mathematical proof, because if you make a mathematical proof, you have to define all your terms. And first of all, you have to define what you mean by a quantum field theory. And already there are books and books trying to make a mathematical definition of what those words actually mean. So it's not a mathematical proof, but it's a proof that in a theoretical physics context, most people would accept as convincing. And then more recently, in fact, even this year, there was a proof based on quantum information theory and entanglement ideas, which actually works in D2, 3, and 4. And hopefully I'll also have time to mention that at the end. Okay, so the outline of the rest of this talk is that I'll talk about everything depends on understanding this object called the stress tensor, or the energy momentum tensor. So although I'll talk about that a little bit next week in my lectures, I'll have to spend some time introducing it here. I'll then describe Zamolodchikov's argument. I'll describe what the A-theorem is supposed to say. I will guide you through Komargodski and Schwimmer's argument, hopefully, and then I will finish, hopefully on time, by talking about the information theory arguments. Yeah, there is an information theory analog of A, which so even though there are no anomalies in 3 dimensions, there is still an information theoretical proof. Yeah. So we're going to be talking about a quantum field theory, a relativistic quantum field theory in general, which is going to be described by some set of quantum fields, which I'll call phi. And we're going to have to look more generally at the theory in curved space. So there's going to be a metric, G mu nu, and this theory is going to be described by some action which is going to be of this form, some Lagrangian density depending on phi, and also the derivatives of phi, which I didn't right down here, and also the metric. So classically, the energy momentum tensor, or what I'm generally going to call just the stress tensor, is the response of the action to a change in the metric, given that the fields themselves also have to transform in a certain way as well. So this is the object which basically appears as the source on the right-hand side of Einstein's equations. So it's the stress tensor is it is symmetric. That's a consequence of rotational or Lorentz invariance, and it's also conserved. That's a consequence of translational invariance. And if we have a scale invariance theory, it's also traceless, and that's the most important thing. So this is in flat space, it is traceless. So when we look at it, though, in a quantum theory, this object has to, because it involves the products of fields at the same point, it must be regularized, and this leads to what are called quantum anomalies. In general, even in flat space, there is a term in the trace which is just proportional to the renormalization group beta functions. So at a general point on the renormalization group trajectories, the trace of the stress tensor is non-zero. That's important. But at a renormalization group X point where the beta functions vanish, corresponding to a conformal field theory, the trace of the stress tensor vanishes in flat space. But when we look at, even when we look at the CFT in curved space, because the curvature of space gives a length scale, then the trace is non-zero. This is what is written at the bottom here. So in 2 dimensions, the trace of the energy momentum in curved space is proportional to the local scalar curvature R times this conformal anomaly number C. Now, in 2 dimensions, the conformal anomaly number C is ubiquitous. It appears all over the place. For example, if you compute the 2-point function of the stress tensor in flat space, it's proportional to 1 over the distance to the whole power times, once again, the conformal anomaly number. If you consider the conformal field theory as a quantum field theory in 1 space and 1 time dimension, and you look at finite temperature, then the entropy density, or the specific heat, is linear in T, in the temperature T. That's not the same T here. T is the temperature here. And once again, the coefficient is proportional to C. So once again, C is counting the number of low energy degrees of freedom. And there is this relation to entanglement entropy, which those of you in the course this morning heard about. I will explain it once again a bit later. But if you look at an interval of length L in the ground state, then the entanglement entropy goes logarithmically with the length of the interval L with a coefficient C over 3. So there are all these different ways that C appears in 2 dimensions. And if you're going to then think about some higher dimensional generalization, then you could in principle choose any one of them and try to repeat the arguments in higher dimensions. Now, the one that I chose in 1988 was this one here. So trying to actually think about the trace in when we put the theory in curved space. Anyway, before I do that, I could describe Zamolodchikov's argument in 2 dimensions, but I don't think I will because I'm running a bit short of time. So it's a, but it was based on the idea that you can in 2 dimensions define C in terms of the 2-point function of the stress tensor in flat space, and then to see how this would then flow under the renormalization group. But I won't go through that. So in 2 dimensions, we have, as I said, the trace of the stress tensor is proportional to the scalar curvature. Now, this is a very special quantity in 2 dimensions, because if we integrate it over some curved manifold, there is a theorem, there's a topological theorem that goes back to Gauss that says that the integral of the scalar curvature over the whole manifold is a topological property of the manifold, which is called the Euler characteristic. So according to this, if we integrate the trace of the stress tensor over the whole manifold, we should get something proportional to C times the Euler characteristic. So this suggests that the way to generalize this number C to higher dimensions, but it only works for even dimensions, is because the Gauss-Bonnet theorem only holds in even dimensions, is to integrate the trace of the stress tensor over some arbitrary manifold M to find this be C, and then to ask whether this quantity for any quantum field theory is decreasing along renormalization group trajectories. Of course, it's easiest always just to choose the simplest compact manifold that you have, so I chose the sphere. So the conjecture was that if you integrate the trace of the stress tensor over a d-dimensional sphere, or then this quantity is going to be decreasing along renormalization group flows, and the ultraviolet C is going to be bigger than the infrared C. Once again, one could certainly check this perturbation theory, but general proof was absent at time. And part of the technical problem here is that, as I said, in the quantum theory, the stress tensor has to be regularized, and in 4 dimensions, it actually contains quartic ultraviolet divergences. These really have to be subtracted off, but as you move along the renormalization group trajectory, the amount that you have to subtract off can actually change. So it made it very non-trivial to actually obtain a proof. So what one has to do is somehow to relate this quantity to something else which doesn't contain these ultraviolet divergences. And that's what Komargodski and Schwimmer were actually able to do. So before I describe their proof, though, I have to sort of tell you that actually the situation was a bit more complicated than what I said. If we look in 4 dimensions, there's not just one anomaly, there are 2. So it's known that for a CFT in 4 dimensions, if you work out the trace of the energy momentum tensor, there is a term proportional to the Euler density, which is called E4. And that's the term which is the generalization in 4 dimensions of the scalar curvature. That's the thing which integrated over the manifold gives you the Euler characteristic. So that's the thing that I was trying to actually propose. So what I should have actually proposed was actually an A-theorem rather than a C-theorem. But there's also this other invariant which is called a Weyl tensor squared, which is this thing here, and the trace can also involve this. And conventionally in 4 dimensions, this coefficient is called C, this coefficient is called A, but this A is the analog of what's called C in 2 dimensions, just to confuse you. Okay, so then one could try to prove an A-theorem, one could try to prove a C-theorem, but it was already known that you couldn't prove a C-theorem because there are already known counterexamples. So then one still had to try to prove an A-theorem. So I'm now going to try and outline Komargodski and Schwimmer's proof. So we're in the situation where we have a quantum field theory with an action S, which is the ultraviolet conformal field theory, perturbed or deformed by a bunch of relevant operators. So these are these with coupling constants, lambda j, these are the operators that are going to cause the renormalization group flow away from the ultraviolet fixed point towards the infrared one. So under this renormalization group flow, we are then going to flow into the infrared conformal field theory. And what we want to ask or to prove is the A corresponding to the ultraviolet theory bigger than the A corresponding to the infrared theory? So the trick is very clever. It's to add an extra scalar field to the theory, which is called, for historical reasons, a dilaton, but that doesn't matter what it's called. We add this extra scalar field, which is called tau. So here's the way that we modify the action. So we we still have the ultraviolet conformal field theory of all the existing degrees of freedom. The coupling now, the way that we form it is that we modify the coupling by this exponential of the dilaton field tau. And then there is this complicated looking term, which is essentially a kinetic energy term for the dilaton. And this has the property that if we make a scale transformation, that is, if we scale the coordinates x, and the fields transform in the way that they did before, but we choose the dilaton field to just scale by a constant, that is, we just add a constant to tau, then in fact all these terms are actually set up such that the whole action is now scale invariant. And in fact it's conformally invariant. So what we've done by adding this extra field is to go back to a conformal field theory, but it's a conformal field theory for all values of this coupling constant F here. So, so basically, this is very clever, but we've changed the theory. So how does this help? Oops. Okay, where are we? Okay, we were here. Okay, so now we want to go to the infrared, and what we're going to do in the, what's going to happen in the infrared in the original theory is that some of the degrees of freedom are going to become massive, so we can imagine integrating them out, and that's going to leave our infrared conformal field theory plus some effective low energy theory for the for this dilaton field that we have added. So because though the total theory is conformally invariant, the A anomaly in the ultraviolet is going to be the same as the A anomaly in the infrared for the new theory. So that so in the ultraviolet we started with this A of the UV CFT, that's the same as the total one, because in the ultraviolet you can show that the dilaton decouples, and that's because the whole theory is conformally invariant, that's the same as the total A in the infrared. But in the infrared you can then, after you've integrated out these massive degrees of freedom, you can show that once again that the dilaton couples, and so the A will be the A of the infrared CFT, which we're trying to get at, plus the A of this effective action for the dilaton. So if we want to show that this is bigger than this, all we have to show is that the effective A for the dilaton is positive. Okay, so then it's just a matter of trying to determine what is the effective low energy theory for the dilaton. And the amazing thing is that that's completely determined by principles of scale invariance and so on. So this is the part of the calculation that I'm not going to go through because it gets rather technical. But what one can basically show is that the effective theory for the dilaton is basically this kinetic term, which is always there, plus an additional term which is called S prime. And this S prime has this complicated form here, but this term, which is linear in the dilaton field, just reflects the fact that this is just the anomaly that we wanted, that the variation of this with respect to tau is just like a scale transformation. So the expectation of T mu nu is proportional to what's in here. Okay, so this is just what we expected. But in order to make this whole thing consistent, we have to add an additional term here where this A dilaton appears multiplying this complicated set of terms here. But the amazing thing is that if we now go from curved space to flat space, all these terms go away except for this term here, which survives in flat space. So what we've done is to relate the coefficient of T mu nu in of the trace in curved space to some 4-point coupling of the dilaton in flat space. So the low energy theory of the dilaton in flat space now has this kinetic term, and then something which corresponds to dilaton-dilaton scattering, because it's fourth order in tau. And then if you work out the dilaton-dilaton scattering amplitude from this very, very simple Lagrangian here, you basically find that it has S form here, and then standard particle physics unitarity arguments then imply that this amplitude has to be positive, and therefore the A of the dilaton has to be positive, and therefore, going back, the A of the ultraviolet theory has to be larger than the A of the infrared theory. Okay, so this was a long train of arguments which really... So this proof uses classic and commonly accepted ideas of quantum field theory, things called anomaly matching, dispersion relations, but it's certainly not as clean or as beautiful as Zamolodchikov's two-dimensional proof. And it's also very specific to D equals 4. There have been attempts to generalize it to D equals 6, but it doesn't seem to. Basically, just there are too many terms in the anomaly, and so on. But it is an argument, and it's a proof, at least it's by theoretical physics standards, it's a proof. Now, in the last 5 minutes, I just want to tell you a little bit about the quantum information types of proof. So this is completely different. Okay, so it's always nice to get a proof which really relies on a completely different physical principle. So we're now looking at a quantum field theory in d space-time dimensions, that is d minus 1 space dimensions and 1 time dimensions, we are thinking about dividing space into regions A and its complement B. We're looking at, in fact, at infinite, at d minus 1 dimensional infinite Euclidean space. There's no curved space here at all. We assume that we can divide the Hilbert space of the quantum field theory into a part corresponding to A and a part corresponding to B. This is actually controversial. So it's not obvious that you can do this for a quantum field theory, but let's assume that you can. As you heard, as most of you heard this morning, you can then, if the whole system is in a pure state size, so that the density matrix of the whole system is this, you can define the reduced density matrix of A by tracing this over the Hilbert space of B. And then the quantum entanglement between A and B is measured by this quantity, which you heard about, called the entanglement entropy, which is the trace over HA rho A log A. Now, it's been known for a few years now that if you take psi to be the vacuum state of a conformal field theory, the ground state, then in 1 plus 1 dimensions, as I mentioned earlier, if A is an interval of length R in an otherwise infinite system, then the entanglement entropy between A and B goes like C over 3 log R. And this is the same C that we've been talking about all along in 2 dimensions. It's not entirely obvious why it should be the same C, but let's just say that in order to compute the entanglement entropy in these quantum field theories, you have to actually go to curved space. You have to introduce what's called a conical angularity into the space-time. And this is basically why the conformal anomaly appears. In 3 plus 1D, it's a bit more complicated. So space is 3-dimensional and time is 1, of course. So if A is the interior of a sphere of radius R, then in the entanglement entropy, you always get what's called this area law term proportional to the area of the surface of the sphere, going like R squared times some non-universal number. And then there's a non-leading term, which also goes like log R. And once again, the coefficient here is related to the A anomaly. And this is precisely the same A anomaly that I've been talking about earlier. And there's an analog of this in 3 dimensions too, which if you ask me about later, I can explain. Okay, so the question is, these are true for in both the ultraviolet and the infrared CFTs, but if we're sort of halfway between, if we're flowing between them, we can still certainly define the entanglement entropy. They won't be given by this straightforward formula, but can you use the way that the entanglement entropy depends upon R to define some kind of effective C, which is going to be decreasing as R increases, and therefore will be decreasing along renormalization group flows? Well, I'll give you the argument very briefly in 2 dimensions. The 4-dimensional argument is much too complicated. So this is the setup that was proposed by Casini and Huerta. So it relies on a remarkable property of the entanglement entropy, which is called strong subadditivity, which is a lot. We know that in thermodynamics, Gibbs entropies have the property of convexity. So this is some generalization of that, or some adaptation to entanglement entropy. And it says that if we have an interval A, and then if we have a region A and a region B, then the sum of the entanglement entropies is always greater than or equal to the entanglement entropy of their union plus the entanglement entropy of their intersection. This is this very beautiful idea of strong subadditivity. So the idea of Casini-Huerta was to apply this in a relativistic situation. So I also explain this. This is space running across here. This is time now. This is real time running up the screen. And our intervals A and B are not constant time intervals, because in a relativistic theory, they don't have to be. We can think of any space-like interval as we can think of this as applying to any space-like intervals. So now A goes from here to here, so its separation is still space-like. These 45-degree lines are the light cones here. So this is A, this is B. You apply this formula to these two intervals here. So A goes from here to here, B goes from here to here. The union of A and B goes from here to here, though, and the intersection of A and B goes from here to here. That's a remarkable thing about relativity. So when you work out if this distance is big R, this distance is small r, you work out the separation of A, it's the square root of R times R. So this strong subadditivity implies this equation here. And if you stare at this equation, it means that as a function of log R, then S of R is a convex function. And that's enough to prove, therefore, that if you define the effective C at a particular distance R to be this, then it will have the property that as R goes to 0, it goes to the central charges in the infrared and the ultraviolet. But because of this convexity property, it always decreases along RG trajectories. So this is the two-dimensional version of what was later generalized to 3D and very recently to 4D. It's much harder to do in higher dimensions because the geometry is just a lot more complicated. So I'm almost at the end, assuming I can make this. So here we go. So just some unresolved questions. We now have c-theorems or a-theorems in 2 dimensions and 4 dimensions I talked about. Also, there's a quantum information proof in 3 dimensions. But we don't have any proofs so far for d greater than or equal to 5. Maybe you would think that doesn't matter, but to some people it does. The other thing is that there was another part to Zamolodchikov's c-theorem in 2 dimensions. He showed not only that the ultraviolet value was bigger than the infrared value, but he also showed that there was this interpolating function as a function of the coupling constants. And these entropic proofs and the Komargodski and Schwimmer proof don't actually give you a candidate for that. So it would be very useful to know precisely if there is an interpolating function. The proofs for d equals 3 and d equals 4, both the Komargodski-Schwimmer proof and the entropic proof require looking at the theory in Minkowski space. Now, why should that be? I mean, if we're looking at a property of the scaling limit of some d-dimensional critical system, some statistical mechanics model, and we want to understand renormalization group flows in StatMech, why should we have to even think about the theory in the Lorentzian signature? So one would like to understand whether there are proofs of these which work entirely in Euclidean space, which would be nice. And once one had understood the answer to that question, one would also like to understand, are there c-theorems for theories which are not relativistic? We have lots of examples, and you've heard about some of these in Uwe's lectures, where we have anisotropic scaling of time versus space. These are not relativistic, but surely renormalization group flows in them exist. We would like to understand whether there is also then a sense in which a theorem or an a-theorem exists for those kinds of theories. So I'll give you some references and I'll stop there. Thank you very much.
So as I understand it, in four-dimensional conformal field theories, you have C, which you can read off from looking at the two-point correlation function of the stress energy tensor. But you could also put the conformal field theory at finite temperature and count the number of degrees of freedom. Look at how the entropy. So that gives you a different.
There are counter examples in both of those.
Right. So I was just wondering, is A in any sense related to counting the number of degrees of freedom by putting the conformal field theory at finite temperature? Is that?
Oh, it's not.
It's not. So it's a different thing. It's
some combination of what I called A and C.
Okay.
Okay. So I said there was an A and a C, and this one, the finite temperature one, for some theories would be a linear combination of A and C, but it wouldn't always be that even, And there are counter examples too. If you wanted to pose that as a, for a 3+1 dimensional CFT, the specific key goes like T cubed or something. That's just the Stefan Boltzmann law, actually, so you might try to use the coefficient of that to define something which was hopefully
So is there any analog of a-theorem for CFTs without a conserved stress tensor?
Without what?
A conserved stress tensor? Conserved stress tensor.
Oh, a conserved stress tensor. Ah, thank you. Well, so the conservation of the stress tensor just corresponds to the theories being translationally invariant, right? So So most of even the anisotropic theories that we would be looking at would probably still be translationally invariant. So if you look at somehow like a system with impurities, impurities will break the translational invariance, and then the stress tensor will be conserved, right? But then if you do some quenched average over the stress tensor will not be conserved, but if you do some quenched average over the impurities, then you can get the translational invariance back again. So I don't know of any. So there are examples where you can break the translational invariance by inserting a boundary or a defect. And if you do that in the right way, then you can still have a c-theorem for the bulk and a c-theorem for the boundary also. So that can work.
I had one question. So, in other examples of like lattice models where one can actually compute this entangled entropy exactly?
Yes, for example, but they have to be exactly solvable models. For example, the transverse isomorphism, for example.
Okay.
But at some point, you still have to do a numerical calculation. I mean, in principle, you can compute it exactly, but you end up with integrals that you can't do analytically, but that's okay.
Okay. But I mean, at least can you show like log r and r square, like logarithmic dependence with
Yes.
size? I mean, at least that you can show
That
exactly.
you can show,
Exactly.
yeah, but at some point it's numerical.
Okay.
Yeah, but it's very easy. I mean, for a lot of these 1+1 dimensional lattice models, using density matrix, renormalization group, and that kind of,
Okay.
it's very easy to compute numerically anyway. So,
Okay.
and then this log R behavior is understood. In fact, that's the most accurate way of estimating C for these theorems.
Okay. Okay, so if there are no other questions, let's thank Professor Cardy for his colloquium.